وعليكم السلام ورحمة الله صبحك الله بالنور.
To begin with, are just sort of something that we can do in the next period of classes. Today we're starting with the flat plate collectors. This is going to take maybe several classes from us, 4 to 6 classes. So I would think that maybe next week on Monday, we can just make the whole class as some sort of revision or like a problem session or so that we have some sort of a link that would be needed from chapter 1 to chapter 5, which would be included in the exam, which is also some sort of a reminder of the foundation that's laid to this chapter 6 onward. So that will be the plan for next Monday, inshallah. You have homework in your hands, which we said that we agreed that it will be submitted on Wednesday. I'm going to post another homework today, inshallah. That will be having like limited problems, maybe 3 problems or so, that will be only on chapter 5, so that it can help you with the preparation of for the exam, and it will be due next Monday, and it will be Monday, no extension, so that I will need to post the solution before the exam, so that you can have a look at, inshallah.
Doctor?
Yes.
Speaking about the homeworks, I have noticed, and even my colleagues, that the second homework, its grade is a little bit low, and I'm not sure why, because I have solved many of the questions near the, I am sure that it's near the correct method.
Yeah, I noticed that as well when I'm seeing it. So that's why I'll be sending you by email for everyone his graded homework. Have a look at it and let me know by Wednesday if you think something is not correct, so that we can get back to the grader. Is that okay?
Sounds great, yes. Thank you.
Fine, okay. So I'll be doing that. Maybe tonight, inshallah, after my evening class, I'll be sending you by emails the first 2 homeworks, number 1 and 2, so that you can see them. And in case you have a concern or something, please raise it to me, just to make sure that you are fairly graded.
Doctor?
Yes.
In our midterm announcement, you said it's 7 p.m. 23 March -21 Tuesday. Which one is it?
Oh, it's 23rd of March. 21 is the year, 2021. So according to the registrar site, it's 23rd of March, which will be next Tuesday. Okay?
Okay.
Yeah, it's confusing talking about 21, but it is the year, it's not the day. Okay, so today we'll be starting to talk about the first application that we're going to have related to solar energy conversion, which is the flat plate collector. This is the one of the most commonly used ways for utilization of the solar energy on the domestic level, meaning that many of the homes, when they are using solar collectors, they are considering the flat plate collectors. It is the easiest to manufacture. It is definitely the cheapest in terms of price, and even the easiest to make. I mean, somebody can decide to make his own flat plate collector. It's not that easy to do that. It's not trivial, but it's something which is doable. And there are so many attempts to make flat plate collectors for domestic level. And in many places, including I've seen in Dammam, for example, houses where they have flat plate collectors on the top of the house, on the roof. And that's for the purpose of heating water. I wouldn't say for house heating, because here it's I mean, we can seldom find days where the weather is too cold, at least for our area of the kingdom. But for heating the water, this is a commonly used way or commonly used device to be utilized. And I would recall one of the projects that we have done, maybe that was 5 years ago or so, talking about the possibility of utilization of flat plate collectors for water heating, for houses, for hospitals, for hotels as well, as a way of reducing considerably the consumption of electrical energy, as well as the consumption of boilers in large installations like in hotels and in hospitals. They need lots of hot water. So what they do is that they have boilers. The boilers are using fuel, diesel in many cases, that is being burnt to heat the water, and then the water passes in pipes into different rooms. So a very good replacement for that. Of course, the diesel is, or using boilers is going to be the cheapest alternative for heating the water, but it's the alternative that results in some environmental footprint in terms of carbon dioxide, which is resulting from the combustion, and this is liberated to the atmosphere, contributing to the global warming. So the issue of replacing this by solar energy was an initiative that I hope it would materialize, and we can see more and more of solar plate collectors in future. Actually, I was also hoping or dreaming that one day we are going to have several factories that are producing flat plate collectors or solar collectors in general. I know that there are some, like if you check Modon, which is the website for industrial areas like Dammam Industrial Area 1, Dammam Industrial Area 2, 3, or the various industrial areas which are located in many places or many cities within the kingdom, you'll find, for example, in Dammam that there is one factory which is producing flat plate collectors. Saudi Ceramic, Al-Khazaf Saudi, is also producing flat plate collectors. If you are in the Eastern Province and you went for the exhibition of Al-Khazaf Saudi somewhere in King Khalid Street in Khobar, you can find that they are having 2 types of flat plate collectors, as far as I remember when I visited once, looking for flat plate collectors, and different companies here and there. But I'm talking about the producers, the one who have factories, and factories are producing this kind of collectors. They do exist, and a flat plate collector can heat the water up to a temperature of close to 100 degrees centigrade. If you are going to talk about domestic use in our homes, we need water somewhere between 40 to 60 degrees centigrade. I mean, this is basically for the domestic level and or even the service level in terms of hospitals and hotels. So that's something which is can be done easily, since we have a good amount of sunshine over the kingdom for most of the year. So that was an intro, just saying that how close the utilization of flat plate collectors is to us. I mean, that it's something which is reachable, it's available in the local market. And by the way, there is some place in the kingdom. I was hearing from one of our previous colleagues who's specialized in metallurgy. He said that some sort of the sand of the highest quality is existing here in the kingdom. And this sand can be utilized for manufacturing the glass. And we have seen, while we are going through the previous chapters, that there are types of glass that are having special characteristics for flat plate collectors, and these, or for collectors in general. And this glass, or this kind of glass, can be manufactured locally from the quality of sands that we have. So a solar collector is a special type of heat exchanger where basically the heat is coming from the sun. It transforms the solar energy into useful heat. It differs from conventional heat exchangers in terms of, for conventional heat exchangers, for example, you have a hot fluid which can be used for heating a cold fluid. The hot fluid can be hot oil or hot water or even combustion products, which are hot gases. But here, the source of energy is coming by solar radiation from the sun. So for our application of solar collectors, we rely on the input energy as solar radiation coming from the sun. Whereas in other heat exchangers, which are fluid to fluid heat exchanger, basically radiation would be neglected, and the most significant mode of heat transfer is going to be convection, except for boilers and furnaces, if we are going to consider them as source of or a sort of heat exchangers where the hot fluids are basically combustion gases. In solar collectors, the energy transfer is from a distant source, which is the sun. At best, it is at a solar flux or a heat flux of about 1,100 watt per meter square. If we did not talk about optical concentration, which is something that we are going to talk about in the previous chapters, talking about that, we can increase that by concentrating the solar energy in, for example, parabolic trough collectors or in paraboloid sort of a dish or so. The wavelength which is covered by the solar energy is somewhere, as we agreed upon previously, between 0.3 to 3 micrometer, which is shorter than that of the emitted radiation from most energy absorbing surfaces. So the analysis of solar collectors is presenting a unique problem of low and variable energy fluxes, and it has large importance of radiation as the major mode of transfer of heat there. Flat plate collectors can be designed for many applications that require temperatures to be heated up to values of 100 degrees centigrade, above the ambient temperature. They have the possibility to use the beam radiation, diffuse radiation. They do not require tracking, and that's why they would need low maintenance, and they are easier to manufacture and cheaper in price. They are simple mechanically, as you will see. It's just an absorbing plate and one or two covers and tubes, which are basically attached to the absorbing plate, or channels, tubes for heating liquids and channels for heating gases, water, air, for example. The major application of these units is for solar water heating, building heating, air conditioning, and industrial process heat. The passively heated buildings, the word passively heated buildings, that's something that you can see a lot in the West, in Europe, as well as in the United States, for example, where you can have many of the houses are having what they call a sunroom, which is a room that has the roof and the walls are basically made of glass. Why is that? Because as the solar energy comes, which is not coming as frequently as we are having here for these places, then greenhouse effect would be there, and the sun would be a source of heat to heat these rooms, and then people would sit in these rooms in the winter so that they can enjoy the sun and get some sort of heating without using any devices to heat the place. And that's why they call it passive heating. So you are getting heat without having to utilize or spend energy to generate that heat. And as an application, the passive heating systems can be seen in chapter 14 of the book. The importance of flat plate collectors in thermal processes is in a way that will be treated in considerable detail in this chapter, so that we would understand how its components function together, how the heat transfer takes place, what are the modes of heat transfer that are there, and why you are using several components. Like, for example, what is the use of the covers? Why sometimes one glass cover? Why two glass covers? So these are things that we are going to establish a knowledge, or at least discuss in this chapter. In many cases, for practical reasons, the analysis of flat plate collectors is simplified to very simple form so that they can be used easily by engineers in terms of evaluating the performance, design, or even comparing between different types or different manufacturers of flat plate collectors. The last sections of this chapter is going to talk about testing the collectors, using of the data, and some practical aspects of manufacture and utilization of heat exchangers. The costs are going to be considered in the chapters that are talking about the applications. Probably toward the end of this chapter, I can share with you some of the specification sheets that are available for flat plate collectors, and even the kind of certificates which are issued by a third party, which is basically some sort of independent agencies that do the analysis or the test for the heat exchangers, and then they provide some sort of a sheet that would be required from manufacturers as they are selling their heat exchangers to have this sheet in. So people would know, for example, what is the efficiency of the solar collector and how the efficiency is changing with the temperature. And this is normally something that will be needed by anyone who buys the solar collector to see how good the solar collector in the application that he wants, depending on what is the temperature of, say, water that he needs to heat. What we see here, the figure in the bottom, is a typical flat plate collector, which is having a double glass kind of a cover. The black thing that we have here in the bottom, which is this sheet, is what we refer to as the absorption plate, which is this one. So this is the absorber plate. This is the one that receives or absorbs the solar energy in, and it gets heated. And because of its heat, definitely it receives the heat by solar radiation. So the heat by radiation is coming. It passes through the glass, it transmits through the glass, reaches for this plate, the plate gets heated, and then it conducts heat by conduction through the whole plate. So the plate is going to have somehow uniform temperature, not exactly uniform. We'll be looking at that in details. And then the tube surfaces are going to be, or the tube walls are going to be heated, and then they are going to transfer heat by convection to the fluid which is inside. To protect this energy from being lost, the thermal insulation is being applied here. There is thickness of insulation, as you can see here, to eliminate or reduce the energy escape or the heat loss to the surroundings. There are a couple of glass sheets. Typically, in most of the collectors, it's only one sheet. And the sheet that we have here is basically to eliminate the transfer of energy from that hot plate to the surroundings. So it is utilizing the greenhouse effect so that the surface of the plate would be at a temperature of maybe 100 or so, maybe less. So it's a long wavelength radiation. And we know that glass is opaque to long wavelength radiation. So it will not transmit energy coming from the hot surface to the surroundings. It's going to keep the energy inside. This is one thing. The second thing is that we have air here in this area. And if the thickness, if the distance between the glass surface and the plate surface is small, then there's no way for the air to circulate. So there's no convection heat transfer in. It would be only conduction in the air, and air has a very low thermal conductivity. So we are protecting this surface from heat loss to the surroundings by radiation due to the glass, by convection due to having a small distance here that will not allow circulation of the air, and by conduction by utilizing air as an insulator. And you know that the best insulator ever is air. Even when we are talking about the fiberglass kind of sheets that are used in building insulation, the good thing about the fiberglass is that the air pockets that are inside, you should have air pockets. And the air pockets are isolated and separated so that you don't have a continuous media of the air to allow for circulation. So the key for having better insulation of the fiberglass sheets is that they are having air pockets inside and utilizing the low thermal conductivity of the air. Air has a thermal conductivity in the order of 0.025 watt per meter Kelvin or meter centigrade. Glass, for example, has a thermal conductivity of 1 or 0.9 something. So that tells you how effective is air in working as an insulating material. And that's something that for conduction, we normally try to maintain and make use of. I do remember in one of the years, that was maybe more than 10 years ago, even I had a master student who was working in the issue of reducing the energy loss through the building walls. And our main concern was to redesign the brick tabuk so that we can have like pockets of air inside it like this. And the thickness of these air pockets would not exceed a value of, say, 25 millimeters or so. And the smaller, the better. And when we have a special design of this kind of bricks, then you don't need insulating of fiberglass, because this is going to be a very good insulator for the analysis. And you'll see that some of the companies are producing some sort of bricks which are close to the ideas that we have mentioned. Air heaters are basically the same concept as you can see here in this figure. Here we are using tubes which are blue in color here because we are thinking that liquid will be there. The liquid is most probably water. Sometimes they use ethylene glycol instead of the water. The reason is two things. Number one, to avoid corrosion, so that you don't use water if you are afraid of corrosion. And the second thing would be, as the temperature gets very low in many places where the temperature go below zero, water might solidify, it can turn to ice. So they use ethylene glycol so that it will keep on in the liquid phase. So the tubes here are circular, and this is basically for water or for oil or for ethylene glycol. If you are talking about heating the air, then instead of having tubes, we are going to use channels. So it'd be something with rectangular cross section which are placed here and the air passes through. So that using channels is going to reduce the friction losses, and accordingly, you are not going to need a lot of pumping work to drive the air through. Although there are some types of solar collectors that do not need any pumps or fans or blowers, but which are called the thermosiphon collectors. We'll be talking about them a little bit later. But in case of replacing, or instead of using water, if you need to heat the air, then we better use higher or bigger cross-sectional area for the air to pass through. Flat plate collectors are always stationary. I mean, you can seldom find, or you cannot find a flat plate collector on a tracking mechanism. Tracking is costly, and whenever you are thinking of flat plate collectors, you are thinking economically that we need to have the best operating system with the lowest price possible. So you are going to go for flat plate collectors, and you're going to mount the flat plate collectors on a fixed position on top of the roof, for example, where you optimize the orientation. For example, if you are going to put it here, then you are going to make it due south, facing south, and at an angle which is equal to the latitude of the city. And this is it. This is the best position that you can put it in. It's not the best position in every day of the year. It may change from season to season, but for all year long, if you need to fix it, that would be the best position to remain at. The analysis that we do, we always assume that we have a steady state condition. Although the nature of solar energy is not. You know that if you follow the solar energy or the energy flux, it starts from zero at dawn, it reaches the maximum at noon, and then, or the solar noon, and then declines again until the sunset. But it is normally used to be cut into intervals, and the intervals would be of 1 hour. We'll be talking about that in details. So normally we consider like an energy balance on a steady state basis, which is provide some sort of a useful energy gain calculation, estimation of the thermal losses and the optical losses from the solar collector. Up to chapter 5, we have used equation like equation 591 that calculates how much is the energy absorbed by a collector per unit area, which is the expression S. To remind you, the S has 3 components. One of them is the beam component, one is the diffuse component, and the third is the ground reflected one. And we had an example that was a detailed example, maybe 2 examples we took in calculating the value of S. And this is basically is a foundation to what we are doing here. But this is not the whole story. This is only a part of it. The second part of the story is, this is the energy gain. What about the energy loss? And if you are going to apply the first law of thermodynamics, like the energy in, if you are talking about a steady state condition, we say, and there's no energy generation. So the energy in is equal to the energy out. And hence, we can make use of applying the first law of thermodynamics in estimating how much would be the useful amount of energy utilized in the system. For example, you have energy coming from the solar energy as S absorbed by the solar collectors, but you are losing part due to the loss by convection, radiation, and conduction to the surrounding. The net amount is the difference between them. And this net amount is the energy leaving the solar collector with the fluid, which is being heated. And the equation that represents what I just mentioned here is the equation which is given below here, equation 621. QU, the U here stands for useful energy, is equal to S into the area. S is the energy absorbed by the sun per unit area multiplied by the area of the collector. So that's the energy N. And the energy escaping is basically the overall heat transfer coefficient UL into the mean plate temperature minus the air or surrounding air temperature. So if you are looking at the energy N, it will basically be this quantity. This is energy N, energy falling into the solar collector by the sun. The energy out is 2 parts. Part of it is useful energy, which is utilized to heat the fluid, and part of it is the losses. So that is basically nothing but talking about that energy N is equal to the energy out, or the first law of thermodynamics applied to a solar collector. Then we shall be looking at each one of these components in details. One of them is something that we know, and we know the details of, which is how to calculate the expression or the amount of energy falling by the solar energy. So now I'm sure that you know how to calculate this. Now we need to look at this part. How can we estimate the kind of the losses? And if we know how to estimate the losses, then we know how to reduce them. And then have your solar collector operating with a high efficiency. Efficiency, again, we are talking about how much is the useful energy that we are getting compared to how much is the incident energy falling into the solar collector. What's the problem with this equation? T plate mean is something which is not easy to determine. So the problem with this equation is that the mean absorber plate temperature is difficult to calculate or measure unless you are installing a thermocouple on the unit and somehow trying to connect the thermocouple to a reader outside the unit, and then without having a leakage of the air or water in or out. So that's an issue that is worth considering. It's difficult to calculate since it's a function of the collector design, the incident solar energy, and the fluid conditions that enter and leave from the solar collector. So a part of this chapter is going to be dedicated to reconsidering this equation, trying to put this equation in different forms so that we can be able to estimate how much is the useful energy of a solar collector. And we try to do it in terms of values that are easily measured. For example, how much is the water inlet temperature? I mean, you can put a thermocouple in the water before it gets to the pipe and after it leaves the solar collector. So you know what is the energy and temperature in and temperature out of the water, for example. And what we are going to define as a heat removal factor that can be evaluated analytically from the basic principles as well as from the experiments. So we're going to put this equation in a form that would provide us with the useful energy as a function of temperature of the fluid and what we call the heat removal factor. This equation is an energy rate equation. In SI system of units, it is going to provide us with Q in terms of watts, which is joules per second. S, as we have seen in the calculations in the previous chapters, can be calculated as in terms of watt per meter square. But definitely the overall heat transfer coefficient is watt per meter square Kelvin or watt per meter square centigrade. It's the same. The point here is that changes in the conditions, for example, how does the solar flux changes? It does not change second by second. It's probably better to express it as it being changed at hour by hour. So we take the average of the hour. You have seen in our previous chapters in chapter 2 and chapter 2, basically, we were talking about the daily average and the hourly average. We did not talk about the average per second because it doesn't make sense. It does not change significantly second to second, which means that we will need to estimate the kind of useful energy on an hourly basis, not on a second basis. This is why you'll find a term of this equation should be multiplied by 3,600, which is the number of seconds in an hour. If you are going to look at the weather conditions, you can never find a weather station providing you temperature second by second because it doesn't make sense. So it may give you an hourly based calculations. So what you are going to do is as if you are averaging your measurements over a period of hour. So the time basis is going to be basically for the solar applications on taken as hour rather than a second. So to do that, as I mentioned, we are going to multiply part of the equation, for example, that takes care of the overall heat transfer coefficient into the temperature difference by 3,600 so that it will be all in or provided on an hourly basis. The hourly basis is not the standard of the SI. So, but it has been almost some sort of a convention to use it with solar collectors. So it's been accepted to be utilized with solar collectors. Otherwise, we would just take the values and integrate it over an hour, which is, again, it's the same thing. So we do not really have a time period less than 1 hour because this is the smallest interval where weather conditions in terms of temperature, wind speed, or solar flux are being measured. So the integration can be done assuming that the value of the energy absorbed by the plate S, the plate mean temperature TPM, and the air temperature are remaining constant over an hour period. So the form of the equation is the same. It's only that we're adjusting it, and instead of being per second, it should be per hour. And to avoid the confusion here, because we know normally when we are using the value of Q, we are using it as in watts or kilowatts, which is basically joules per second. And to give the same meaning of heat transfer rate, we are going to use the expression of either Q dot U or QU, where U here stands for useful energy. And when we see to solar collectors, we would just figure out that it is something that has been done with taking the time duration or the time domain as unit as 1 hour. That's why we don't use the expression of G or I in this equation, but use the expression of S. And we know that from previous calculations that S is the amount of solar radiation absorbed by a plate or the absorbent plate in the flat plate collector. So that explains why the 3,600 part is, or figure is going to be in many cases found in these equations. The alternative, as I mentioned, is to use the integration. For example, what we see in front of us here is a definition of the efficiency of a solar collector. And this is a quite important parameter that we are going to use for solar collectors. Actually, the specification sheet that you can see for any flat plate collector that you buy the flat plate collector, and before you buy it, you are going to look at the specification sheet and look basically at the expression of the efficiency. The expression of efficiency is you can see here, this is our educational basic of the mathematical formulation of the efficiency of the collector. That is the integral of QU with respect to time over the integral of the incident energy, GT solar energy, the irradiation with respect to time. So this is basically on the top, we're talking about the useful energy, and in the denominator or the bottom, basically you have the amount of energy N to the solar collector. And by definition, efficiency is energy out, useful energy out divided by the energy N. But when you are going to see that for existing flat plate collectors, you'll find it given in two forms. Either given the efficiency as a straight line approximation, and you are given the intersection with the y-axis and the slope, or it can be given in terms of a three-term polynomial, and it's all up to you to use either one of them. The efficiency issue here is again of important practical application. Not only that it has been simplified to a straight line formula or to a polynomial of three orders or three parameters or to the power of 3 or to the power of 2. The point here is when you are practically going for a solar collector, the efficiency is not the only option that you would do for a flat plate collector. But there's another very important option, which is how much is the collector? I mean, I can find a high efficiency collector very expensive. I may then turn it down and buy another collector, which is at a lower efficiency if it is cheaper. The point at the end is how much am I going to pay for the whole thing? I remember one of the applications or one of the projects that has been funded by the European Union in 2003 to 2006. It was by a German scientist who was interested in coming up with a system for using the solar energy to desalinate the seawater and turn it into sweet water. He was using a technology which is called humidification system. This is not the point. But the point is he found that more than 50% of the capital cost of his installation is going in buying or spent in buying solar collectors. This is way too expensive, and it's going to affect the price of the water that he is going to desalinate and sell. So practically speaking, he's going to come up with water which is more expensive than other sources, and then he will not be able to operate his project. So the point would be, he came up with his own design of the solar collectors, where he replaced the glass by polyurethane kind of sheets. The solar collectors were much less in efficiency, but they were much, much cheaper. And he said, I can use more and more of these collectors instead of having a smaller number of collectors with high efficiency and high price. So the point here, when you are going to make your selection, it's not enough that you go for the highest efficiency of the solar collector. This is not enough, especially if you are going to put solar collectors on the top, on the roof of your house. Then you don't have a problem with utilizing 2 collectors only with high efficiency. You can use 4 or 5 with lower efficiency. And anyway, at the end, you are going to get the required amount of energy that you want. It becomes significant then if you are going to buy a land, and this land you are buying is just for installing the solar collectors. Then you have to account for the price of the land, and having smaller land, it will be cheaper. So it's a matter of trade-off. You need to calculate the economics well, and based on that, you can make your selection. So the key takeaway from this slide is it is not necessarily that you always, every time, go for the high efficiency solar collector. No, the economics are playing the major role in selection of the solar collector there. When we come to the analysis of the solar collector, look at the picture or the figure at the bottom here. This is basically what we'll be looking at as in determining the heat transfer model. We can represent that in the form of heat transfer resistances. There's energy falling in. The energy has to pass through the second glass cover. This is radiation. And then it will go through the first cover. And then it will fall into the absorbing plate, which is this, as it does here. Now, these are two glass covers. In between here, what is there? What's in between?
Air.
Air, yes. And here, in between also, we have air. So the mode of heat transfer that we are going to see here is going to be a combination of convection plus radiation. If we are able to reduce the convection by reducing the distance between the plates, you know, when we are talking about convection here, we are talking about natural convection. And natural convection is basically given as a function of Rayleigh number. Rayleigh number is a function of the distance between the plates. If the Rayleigh number is below a critical value, the critical value may change from book to book. Some books would say it's 1,000, some book would say it's 1,800. So anyway, if you are going to go for a Rayleigh number less than the critical value, then you are suppressing the convection. Convection will not be effective, and it's going to be replaced by conduction. So, which means that at the bottom, we are looking for resistances here between the two glass plates and between the glass plate and the collector that is given in terms of convection, conduction, and radiation. Probably I mentioned to you before that the word convection is originating from con, which is conduction, and vection, which is coming from advection, which is the energy transfer due to the fluid motion. So when we are talking about convection, then conduction is a part of it anyway. So the point here is that when you are looking at the energy falling and the energy which is being lost by the surface of the solar collector to the surroundings, again, we have convection to the air and we have radiation to the sky. So a combination of convection and radiation is always going to be there. We are going to assume we have a uniform temperature of that plate, uniform temperature of this plate. Can we assume uniform temperature to this plate? We are going to see that. And then, so this is, after that, we try to reduce the losses. The losses basically are losses by conduction through the insulating material. And here you have losses again by convection and by radiation to the surroundings. And there could be losses from the edge as well. So our target here is to maximize the energy which is falling on the absorbing plate, so that this is the heat coming in, and minimize the losses to the surroundings. These losses are basically modes of heat transfer that we need to look at. And one of the ways to look at these modes is through using what we call a thermal circuit. Let's now focus on this absorbing plate and try to see how we can look at the energy in this absorbing plate. You have taken in heat transfer, you have used the book of Encropera and DeWitt, I would assume. And in chapter 2, you have studied extended surfaces. And one of the problems at the end of the surface is talking about the solar collector and looking at the extended surfaces as a part of the absorbing plate. I'm not sure if you have passed through this this problem. The last time I taught heat transfer, it was several years ago, so I'm not sure if this problem is being taken as a part of the homeworks anymore or not. But it's interesting to look at this. I mean, this is the plate, as you can see it here in figure A. And in figure A, you have a plate which is receiving energy from the sun. So that is basically being heated. Heat is radiated to this plate. And this is basically the most precious part of the solar collector, because this is the receiver. This is the absorbing plate. This is the one that will get heated first. And after that, it will transfer heat to the fluid inside the tubes. Now, it is being heated, but the heat is taken away by the fluid, which means here that the fluid is working as a coolant for this plate. So the temperature of the plate is going to be less whenever it comes in contact with the fluid, which is basically this area. Why? Because the energy which is transferred here is taken by the fluid. So this area is going to be of lower temperature. So there is symmetry here. In between the two plates, the highest temperature is going to be in the middle, and the temperature is going to drop as you are going to the sides, which is what you see here. If you look at the temperature profile, we assume that the tubes are having fluid with uniform temperature for the same x. This is the x direction. And if you need to move in the y direction, it will be this. So this is x and this is y. For the x direction, we assume the fluid at the same area, at the same location here, at the inlet, for example, is constant in temperature, uniform temperature, not constant. And then its temperature increases as you are moving here, because it continuously receives heat from the plate. So, but for any location x, the temperature of the fluid is uniform, and this is why you see this is like a horizontal line here. So there is the hottest part is in the middle between the two tubes, and the lowest temperature is the constant temperature that is transferred to the fluid. So this is how the temperature distribution in the x direction is looked at, which is basically is this. This is the highest temperature in the middle of the tubes, and at the tube we have a uniform temperature here and here, and this is the lowest temperature in this profile in front of us. What about when we are moving in this direction? The fluid enters at a temperature of, say, 25 degrees centigrade, and then it is heated to something like 80 degrees centigrade at the exit of the solar collector, which means that there's an increase in temperature in this direction, which is seen here. The temperature increases because of the heat gain that is going to the fluid as the fluid passes inside the tubes in the tube longitudinal direction, as you can see it here. So this is basically the kind of temperature distribution that you would anticipate when you are having a flat plate collectors where tubes are welded into it, as you can see it here. The transfer of heat through the plate is by conduction until you reach to the surface of the tubes. It is by conduction through the tube thickness, and then by convection from the inner surface of the tube to the fluid which is passing inside. The fluid could be water, it could be air, it could be any fluid, liquid or gas. This slide is basically talking about the things I just mentioned, or the description I just mentioned here in terms of the how the heat is being distributed and how the temperature is changing within the plate and in the tubes. To do the modeling, as usual, when you are talking about a model, what does a model mean? A model means a mathematical way that you can represent a physical process. The physical process here is having a solar collector and having a fluid that will be heated by the energy coming from the sun. In order to convert this into equations, like previously, you have seen the first law of thermodynamics expression, which is written for the flat plate collectors. Now, the point is, to do that, we need to have some assumptions that are going to make our analysis easier. The assumptions are the performance is steady state. Steady state means that we are doing the analysis for an hour, where through this hour, the kind of energy coming from the sun is fixed, temperature of the air is fixed, and mean temperatures of the plate as well as the water inside or the air inside is going to be constant. And then In the next hour, they are going to be different, but they will be constant all over the hour. So they are talking about the average value for an hour. Within the hour, it's a steady state condition. The sheets and the tubes are basically parallel. So we have the glass sheets are parallel to each other. They are parallel to the absorbing plate, and the tubes are parallel to each other. There are headers, because when we are talking about tubes that are extended from one end of the solar collector to the other end, this is one tube, and this is another tube, and this is a third tube. How the water is coming and leaving from the tubes. There should be a header here. These headers receive the cold fluid here. It distributes the cold fluids into the tubes, and there is another header here that collects the hot fluid and gives the product. This is typically what you see in a flat plate collector. Now we are going to neglect the changes that are going to be here inside the headers. So as if the tubes are receiving the energy or flow of the water in and taking the flow of the water, for example, out. So the headers cover an area which is neglected or can be neglected because it's too small. And the headers gives uniform flow to the tubes, which means that the flow rate here and here and here are equal. The temperature here is the same. The flow rate here leaving is equal, and the temperature is the same from leaving from all the tubes. There's no absorption of solar energy by a cover insofar as it affects losses from the collector. So here the cover is not really contributing as an absorber of the solar energy. I mean the glass cover. The heat flow through the cover is one-dimensional. So if this is the flat plate collector, then the energy falling into it is falling in one dimension. We are not going to consider X, Y, and Z. It's only coming in the Z direction. There's negligible temperature drop through the cover. So the cover is assumed to be uniform in temperature. The temperature is not varying from one location to the other. The covers are opaque to infrared radiation. So they are not allowing the long wavelength radiation from the plate, the absorbing plate, to the outside. This is the greenhouse effect. One-dimensional heat flow through back insulation. In the insulation that we have in the back, if this is the flat plate collector cross-section area, and here's the insulation, and these are the tubes, which are covered by the absorbing plate, then the heat transfer here is moving in one direction. So it's not a 2 or 3D case in terms of heat transfer, and that's for simplicity. The sky is considered as a black body for long wavelength radiation at an equivalent sky temperature. This is for the heat losses from the upper surface to the sky, while assuming the sky is at a uniform temperature. That could be the same of the outside air or ambient temperature or different. It depends. And we'll see in this chapter how the differences can be almost insignificant. Temperature gradient around the tubes can be neglected. We assume uniform temperature in and around the tubes. Temperature gradient in the direction of flow and in between the tubes is treated independently. So that's something that we're going to deal with alone. I mean, a part of it is what I just mentioned, that in the direction of flow, normal to the paper here, this is the inlet. If I put like a 3D figure of it, there are tubes here. And in this direction, there is an increase.
دكتور
We still can't hear you.
Can you hear me now?
Yes.
Yes.
Yes, sorry, it's just all of a sudden that the connection has been lost. I just found it when it's trying to reconnect. Where did you hear me up to? Which one of these items that we're discussing? Are you following? Which assumption that you heard the last?
When you said the temperature inside the pipe, something like that, it will be.
Oh yes, it will be treated. Yeah, the temperature inside the pipe here, which is basically increasing, but it's going to be treated as independently or separately. The properties are going to be treated as constant. As I mentioned, probably that if you are going to use engineering equation solver, it takes care of the variation of the properties. But if you are going to be doing hand calculations, it's easiest to consider properties are constant. Like what? Like the CP, for example, specific heat. You can take it as a constant value. The losses through the front end, which is this, and the back end, which is there, are going to be neglected. Or if we are going to consider it through all the ends, it will be losses to the ambient temperature. And that's something that we can look whenever we get into the detailed calculation of which of it can be considered and which can be neglected. And if we are going to neglect it, is it really insignificant or not? We neglect the effect of the dust and the dirt on the collector because we know if the collector gets dusty with sandstorms, it reduces the amount of energy falling in. And that's something that we're going to neglect, assuming that they are always clean glass surfaces. Also, we're going to neglect the effect of shading, which means that we assume that the solar collector are placed in a location where they are not covered by shade from any adjacent buildings or trees as they are operating. The kind of equations that we are going to have are basically coupled and nonlinear equations, which in many cases would require to be solved in a platform, in a programming, for example, by writing in Fortran or in C or in Java or whatever computer language that you master. And this is normally done by approximations of converting the nonlinear terms into linear ones. This is what we call linearization of the equations, discretization of differential equations using like Newton-Raphson iterative method for solutions. And there's a number of computer programs that are available that can solve system of equations. I mean, there are so many of them. An example is the engineering equation solver, EES, where actually the one who developed the EES is Klein, which is one of the most significant authors of articles talking about solar collectors. Engineering equation solver is a unique program when it comes to applications of thermal sciences, including this course, of course, definitely, because the properties are built in. Actually, it has so many functions that we need for heat transfer analysis that are built in, and it is easiest to utilize in terms of equations writing. All you have to do is write number of equations equal to the number of unknowns at any order, and you don't have to worry about the details of the solution. If you have to write that in Fortran, then you have to define first all the properties, give initial values for all of the variables, and then update the variables. Here in ES, it's all built in. You just need to write your equations there. As long as the number of equations is equal to the number of unknowns, this is it. The program itself assumed initial values, and then it's going to reiterate the solution until convergence is realized. So it is the most convenient when it comes to utilizing softwares or programs easily for solar collector issues. What you see in here is resistances. These are thermal resistances. If you remember, when you studied heat transfer, you studied conduction. And then for conduction over a flat plate, you used to write an expression for the thermal resistance, convection, and used expression for the thermal resistance, radiation, and used an expression of the thermal resistance as well. That's something we probably covered in the revision in chapter 3, revision to heat transfer. But just quickly, if we are going to talk about conduction, heat transfer, conduction is governed by Fourier law of conduction. The integrated form of Fourier law of conduction is saying that Q is equal to K A into delta T divided by the length L. So we tend to put this as delta T over R conduction. And R conduction here will be L over Ka. So that's a representation of conduction. When we come to convection, Q is by Newton law of cooling, HA into delta T. Then it can be given as delta T over R convection, and R convection is 1 over HA. So this is basically the way that we are going to represent thermal circuits. When it comes to radiation, we know that, or we have seen in chapter 3, that we can write radiation as Q is equal to H radiation into delta T. Again, when you are talking about definitely into the area. So when you are talking about radiation resistance, it will be 1 divided by HR into A. So this is the kind of thing, or the kind of expressions that we are going to consider here for the heat transfer modes that would make it easy. Look at the thermal circuit at the left. What do we have here? We have solar energy, which is falling into an absorber plate, which is this. The absorber plate is heating the fluid, resulting in useful heat, which is this. And then it is losing energy, part of the energy lost into the top and part of the energy lost into the underneath. The energy lost at the top, yeah, you have here, this is the plate, and this is the first glass cover. In between there is air, so there is conduction, there is convection, and there is radiation losses here. They are in parallel. So the resistance here is 1 over H radiation from the plate to cover 1, and this is 1 over H convection from the plate to the cover 1. And then from cover 1 to cover 2, there is air inside. Again, there is heat loss by radiation and heat loss by convection, and they are parallel. So of parallel resistances, convection between cover 1 to cover 2, radiation between cover 1 to cover 2. And then cover 2 is exposed to the air. So it is losing energy to the air in terms of convection. This is the convection by the wind expression. And this is the radiation to the sky, which is 1 over HR. So what we have here basically, convection and radiation from the plate to the cover 1, convection and radiation from cover 1 to cover 2, convection and radiation from cover 2 to the surrounding air. This is what's going from the plate upward. What about from the plate downward? You have insulating material. And then you have from the surface, from the lower surface of the solar collector, you have energy lost to the air by convection and by radiation again. So this is basically some sort of a representation of the heat transfer modes within the solar collectors. These two are connected in parallel, we call them R1. These two are connected in parallel, we call them R2. These two parallel, we call them R3. This is just conduction resistance, and these are connected in parallel to make R5. So we have 5 resistances in series, 3 on the top of the plate and 2 at the bottom of the plate. So from the plate to the first cover, a combination of convection radiation. From the first cover to the second cover, combination of convection radiation. From the second cover to the surroundings, it's again combination of convection and radiation. And then from the plate to the bottom, there is insulating material, conduction resistance. And then from the surface of the solar collector, again, a combined resistance in parallel by convection and radiation. So these are the types of thermal resistances that we have for a flat plate collector. And that would make it much easier to analyze when you look at it that way. What we need to look at the end is just try to put it in a form that can be represented by this simple figure. There is energy absorbed to the plate, and the plate is distributing the energy. Part of it is in useful energy, and part of it is losses to the surrounding, and the losses are given by an expression which is represented by an overall heat transfer coefficient. Now we are putting it in the simplest form, and this is what we need to reach at the end. Whenever you are talking about a flat plate collector, you don't have to talk about this resistance and this resistance. Those are in parallel and they are combined in series with the other group. So you don't want to talk about that. You just want to talk about the energy useful that you are getting from solar collector and the losses combined in one parameter. And probably that's going to remind you of equation number one, that when we put the first law of thermodynamics at the beginning, we said that there's energy in, which is S, and there's energy out. Part of it is useful energy, which is this QU, and there's part losses to the surrounding, which is given by overall heat transfer coefficient into T mean of the plate minus T air. So this is basically what we need to reach at the end. So what we need to do is to convert this number of thermal resistances that we see here in this figure into this simplified form where only one expression, lumped expression, is going to talk about the kind of losses that are resulting from the solar collector. What we're doing here, we're utilizing the information that we have gained in chapter 3, the revision of heat transfer course, into several parts that we have. What we see here, the first equation, 641. This is the energy lost from the top from the plate, top of the plate into the cover one, which basically is representing by this part here. We have radiation and convection from the plate to the first cover. So remember, they are parallel and the area is the same. Because the area is the same, we have used this expression for the radiation heat transfer. Sigma Tp to the power 4, T plate to the power 4 minus T cover 1 to the power 4. Temperatures are in Kelvin. This is emissivity of the plate and this is emissivity of cover 1. And this is the convection heat transfer by natural convection from the plate to the surrounding. So this is Newton's law of cooling, and this is Stefan Boltzmann law of radiation. And these two are taking care of the energy loss from the top of the absorbing plate to the glass. Then H by convection from the plate to C1 is convection heat transfer coefficient. To determine this value, you need to get back into the Rayleigh number calculation, which is a function of how much is the distance between the two plates, calculate the Rayleigh number, and then go to the correlation of Nusselt number as a function of Rayleigh number, calculate the Nusselt number. Nusselt number is HL over K, then you can get the heat transfer coefficient H. So just to make a long story short, you're going to follow whatever we have covered in natural convection to determine what would be the value of H here. And then when it comes to radiation, we're going to apply the Stefan Boltzmann law of radiation. These properties are known. The value of epsilon for the plate, epsilon for the cover are going to be known. And then you're going to apply it here and calculate how much is the losses from the top of the absorber plate to the first layer of glass. Sometimes it would be easy to, instead of talking about all of that expression for the radiation, we can just use the HR, or the radiation heat transfer coefficient, or equivalent radiation heat transfer coefficient, so that the heat losses from the top can be given in terms of the value of HR. And that expression, instead of putting it in this form, you're going to put it in that form, which is simpler form, but the HR has to be extracted from here. This basically, you're going to analyze this. This is TP square minus TC square. So it becomes TP to the power 4, I'm sorry. It will be TP to the power 2 minus TC square into TP square plus TC square. And then you are going to analyze this further to TP minus TC into TP plus TC. So your term is TP minus TC, TP plus TC, TP square plus TC square. To put the expression in terms of HR into TP minus TC, then the HR should include this term, and those. And this is basically what you see here. So sigma into TP plus TC1, T square P plus TC1 square divided by the same denominator that we have here. Then you have converted the way that you're writing the Q loss from the top of the absorber plate to that simpler form. You can combine easily these two together. It becomes something that looks like the Newton law of cooling. Then your resistance here is going to be 1 over H convection and H radiation. And that's much easier to handle in terms of resistances. This is the one that you see here. Similarly, you can do the same for the others. So the expression from plate 1 to plate 2 can be written in a similar manner, and a similar manner to this. From the upper plate, plate 2, to the surrounding, again, convection and radiation, so it can be written in the same manner. So now we're trying to make our life easier by finding simpler expressions of the combination of convection and radiation from one plate to the next one. Okay. Any questions so far? I mean, I've not been interrupted since I started, so shall I assume that you understand?
Yes, doctor, it is pretty much clear, at least for me.
So here we're talking about cases where that expressions of heat transfer modes is going to be represented. So the same thing, as you can see, it can be given for R2, for R1, and for R3. Accordingly, the combination of resistances on top of the plate, if this is the plate, P, sorry, we have resistance from the plate to cover 2, then from cover 2 to cover 1, and then from cover 1 to the surroundings. We are talking about 3 resistances. Combining the 3 resistances here becomes easy in an overall heat transfer coefficient. So we can use an expression of the overall heat transfer coefficient to represent these combinations of convection and radiation resistances on the first 3 layers. The 3 layers are, again, from the plate to cover 2, from cover 2 to cover 1, and from cover 1 to the surroundings. Then an overall heat transfer coefficient is going to make our life much easier. The only problem that we have here is that we mentioned that T plate is unknown, which means that necessarily we need to go through an iterative solution to come up with this temperature. And that's why you cannot avoid having an iterative solution for this, for these kind of calculations. And generally speaking, the kind of heat transfer rate, when you are writing it, it will be a combination between any two plates of these. T of one plate minus T of the other plate can be given by an overall heat transfer coefficient difference in temperature over the combination of H and H. I mean, H convection and H radiation. And it's an iterative process that I would think we can begin with it in our next class as an example. So next class, we are going to start with this example. And after today, we had some sort of a long introduction to the chapter. And then after that, we are going to talk about any kind of increment of the information. It will be followed by an example so that it can clarify the point that we are discussing or talking about. So that would be it for today. Sorry, it's been like a narrative sort of a class. I was hoping that we can have like some sort of better interaction, but we can do it next time. Maybe when we solve these examples, I can get you involved in it with me as well as we did earlier in some classes. So thank you, and we'll see you on Wednesday, inshallah.